Okay, so let's see if I can do this. So basically we say that U1 is equal to V1, which is equal to this one. Let's just call it 1, 1, 1, 1. And then U2, which is equal to V2 minus the projection of V2 onto U1. So we have to take the second vector, which is 1, 1, negative 1, negative 1, and subtract the projection of V2 onto U1. So we need the dot product of V and U, so V2 and U1. So I'm going to highlight that. So we need the dot product. That's not what I wanted to do. We need the dot product of this. Is that? No, that doesn't sound right. Oh, I see why. Let's change the order of things. I'm so confused. Okay, so U1, let's make that our first V1. And let's make U2 our second V that we're looking for. And let's swap these. Does that make more sense? Yeah, that makes more sense. Because now I can take the projection of this onto this. That's what I want. And I need to take the V1 dot with itself, and then I need to multiply by the V1 vector, which is actually this vector here, right? So it's actually a multiple of the first vector that we find. That was my error. I think that's what happened. So in the second one, that doesn't matter because we know that this dot product's going to come out to be 0. So we know that U2 dot V1 should be 1 plus 1 minus 1 minus 1, which is 0. So we know that V2 is just U2. But when I was calculating my third vector, which should be U3 minus 2 projections, so the projection of U3 on V1 minus the projection of U3 on V2. Let me write this out and we'll get caught up on chat. This is where I made my mistake. So we need to subtract the U3 V1 dot product, the V1 V1 dot product, but I'm multiplying by V1, which is 1, 1, 1, 1. And then here we need the U3 V2 and V2 V2 dot products, and then I multiply by V2, which is 1, 1, negative 1, negative 1. There we go. Holy smokes. Okay. So what is U3? U3 is 0, negative 1, 2, and 1. So let's write that down. So 0, negative 1, 2, and 1. The dot product of U3 and V1. So U3 we just wrote down, so we need 0. So we need 0 minus 1 plus 2 plus 1. And V1 with itself we know is 1 plus 1 plus 1 plus 1, so we get 4. U3 with V2 is 0, minus 1, minus 2, minus 1. And that's over V2 dot product itself, which again is still 4. So 1, 1, negative 1, negative 1. Okay, so we need 0, negative 1, 2, 1. We have 2 plus 1 is 3, minus 1 is 2. So minus a half. So minus a half of this vector. And then minus, this is going to be plus 2, 3, 4. So plus 1 of this vector. There we go. I think this should hopefully be okay. Oh my goodness. So we need 0 minus a half plus 1. So 1 minus a half is a half. We have negative 1 minus a half. So negative 3 over 2 plus 1. Negative 3 over 2 plus 1 is negative a half, right? 2 minus a half is 3 over 2. Minus 1 is a half. 1 minus a half is a half. Plus negative 1. So a half minus another 1. So negative a half. Okay, so now we have a set of orthonormal vectors would be v1 divided by its length. So these should be over root 4, right? So the length of the vector, so we need 1 over 2, 1 over 2, 1 over 2, 1 over 2. We need v2 divided by its length, which is also going to be root 4. So this one's going to be 1 half, 1 half, negative a half, negative a half. Now, what I want to do here for the vector that we just found, so we want to find the length of v3, which is going to be 1/4 plus a fourth plus a fourth plus a fourth. So we get 4. Wait, is this already a unit vector? Cool, so it's already a unit vector. So v3 is already normalized. So the last vector that we're going to need is 1 half, negative a half, 1 half, negative a half. Holy smokes. Does that work? Yeah, 1 and 3 are definitely orthogonal. We know that 1 and 2 are already orthogonal. 2 and 3, that should work, right? We get a positive, a negative, and a positive. Perfect. So this is the set of orthonormal vectors that we need from the Gram Schmidt process.